Prevent student Thomond village here behind me from flooding, which has happened in recent years. As student engineers, we had no previous experience with either soil mechanics or geology. We were quickly introduced to the soil mechanics triangle, which referred to ground profile, soil behaviour and also appropriate model. We referred to this throughout our project in order to keep us on the right track. Before jumping into the design of the berm, which is going to be located in the green area here behind me, we had to do site investigations in order to discover what kind of soil to be used and the characteristics of it.
There are several health and safety issues that we encountered while doing this project. During the site investigation and digging of the trial pits, nobody was allowed on site without the necessary safety gear. This included a hard hat, high-vis vest and safety boots. A safe soil structure can change dramatically with changes in weather and become dangerous in a short space of time. In general, a trial pit doesn't have a depth greater than 5 metres, but any pit with a depth greater than 1.5 metres should be braced. Other dangers associated with trial pits are people, vehicles and materials falling into them, leptospirosis, contaminated land, methane gases and contact with underground surfaces. Another problem we had was with the water table level. If we encountered a perched water table level and made the mistake of using this as our actual water table level, it would undermine the whole structure from the foundation. In the labs, we also took safety precautions. We wore lab coats and safety glasses at all times, and when obtaining soil samples from the oven, we used steel tongs. We used this as our kind of plan for carrying out things safely. First, we planned how the safety precautions we were going to take. We did them, we checked, and then we acted and did the actual necessary work.
We carried out a site investigation of this site here on Wednesday the 8th of February. As civil engineers, we have learned that safety must come first, so we have our hard hat, our luminous jacket and our hobnail boots. As we arrived to the site the first day, we noticed that the ground was very marshy, and also the presence of rushes around led us to believe that there was a high moisture content in the soil. Also, the presence of a stream running beside the site furthered that belief. There's also been a lot of evidence of recent activity in this site, such as the development of the astroturf pitches behind us, and also the development of a student village just there behind them trees. We dug 2 trial pits in this site. We're standing on one here, and the other one is just down over there. To dig these sites, we brought in a digger who excavated the site for us. And as the excavation got deeper, the profile and the strata of the soil became very clear to us. As the excavation got deeper, we noticed that the walls began to fall in on the side of the dig. This showed us that there was high moisture content and instability in the soils around it. When the dig was finished, we started to study the structure of the soil. We took the measurements for each layer. We noticed that the topsoil layer was 0.175 metres deep. Next was the sandy gravelly layer, which was 2.7 metres deep, and the final layer was a clay layer, which we didn't get a measurement of because it met the water table. We got the water table to be roughly 2.8 metres below the ground level. We also carried out a vein test to get the shear capacity of the soil at this site. Also, while we were at the site, we carried out an MCCSSOOW analysis of the soil. This stands for moisture, colour, content, structure, soil type, origin, other and water table. For the topsoil, we found that it was a moist brown soil made of organic materials. It had an intact structure. Its soil type was topsoil, and the water table was not present. For the grey sand fill, we found that this was a moist grained soil. It was made up of sand and gravel. It had been filled into the site, and the water table was not yet present in this. And for the final layer, the clear layer, we found that it was also a moist, grey, thinly bedded soil. It was made up of clay, and the water table was present at this level.
In order to analyze our soil properties and then design our berm, a number of tests need to be carried out. Here, I will talk about 3 experiments we did in the lab and why we did it. After we took samples of the soil from the site, the first thing we wanted to know is what type of soil it was, or what its classification was. First, we did the weight sieve test in order to find the percentage passing. From this, we determined that our soil is either the fine silt or clay, but it's not specific enough, so we did the plastic limit and liquid limit tests. From the results and formulas, we found the plastic index. We then used this figure on a graph to find out what is the type of soil we were dealing with, which is a clay. The next test we did was the Proctor test. By doing the Proctor test, we will receive results for the maximum dry density and optimal moisture content. These values are found by plotting the obtained data on a graph. These values are required and will specified by an engineer before the construction of the dam. The final experiment I'm going to talk about is the falling head test. By measuring the time for water to pass through a specified volume of soil, we could determine the permeability of the soil. Using this, we could find out the quantity of water passing within the soil over a united time, which helps us to analyze the issue of seepage afterwards. After all necessary tests were conducted and we analyzed the results, we have effectively recognized the material we are dealing with in our berm, and now we are ready to move on to the next stage, design our berm in detail.
On our site, we're dealing with an impervious foundation. This left us with two main design choices. The first is a zone dirt dam. This is where the central core of the dam is constructed out of an impermeable material, and for strength and stability there is two shells either side of this constructed out of a granular material which is pervious. For a round dam, we chose a homogeneous dam. This is when the entire dam is constructed out of one material. For its impermeable properties, we chose clay. The dimensions can be shown here. The height of the dam is 3 meters, which left us with a crest width of 2.8. As a rule of thumb, the upstream slope should be 3:1, which left us at a base width of the slope of 9 meters. A similar calculation is done here, whereas 2:1 on the downstream slope, which left us at 6 meters. Because there is seepage through all soils, we had to incorporate a rock toe. This prevents such failures such as boiling and piping, in which Zhang will talk about later. There are two key requirements of an earth dam. The first, it must be able to impound water, and also it must be able to do this without unacceptable seepage losses. Clay is an ideal material for this. This is due to the orientation and shape of the grains inside the clay. Another important property of the clay is that it's cohesive and plastic in nature. This means that it is able to be shaped and retain the shape when compacted. A negative aspect of using clay is that it is susceptible to swelling. Swelling occurs when the swelling pressure in the soil is greater than the effective stress in the body of the soil. Moisture content plays a major role in swelling and shrinkage of the soil, although other properties are very related to the swelling of the soil.
As we discussed before, seepage is a movement of water through a soil mass. Video here shows how dam fail due to seepage within the dam. Also, considering seepage generates an upward force while it moves. When the upward force on the soil particle exceeds the downward weight, then it tends to be taken away. Because it generally happens at the downstream end of the berm, it will be washed away by the stream. After a while, this term called piping will occur, which leads to the failure of the entire structure. From studying the history, Thomond Dam is an example of this kind of failure. It killed 11 people and cost millions of dollars. Therefore, couple of calculations need to be carried out. First thing first, draw a skilled flow net, then find out this term called factor of safety for piping. Generally, it should be over 5, and it's 12 in our case. In addition, the forces generated by seepage are acting on the base of the berm. It tends to lift the structure up if it's greater than the self-weight of the structure. To avoid that, factor of safety for uplift force should also be calculated using the flow net before the construction of the dam.
We've now reached the end of our documentary. I hope you've learned lots about our dam. I hope you've enjoyed watching the documentary as much as we've enjoyed designing the dam. Thank you.